So I got. My parents say, "Oh, he's so they would just. All this. My own. I don't have it, but I'm just gonna have it up to like. Oh. Yeah. Now it's not social. Like she said, that's just so she got yeah, that works. What? Oh, yeah. Oh, yeah. Yeah. What she's doing. Yeah. Yeah, that's what I was saying. My dad was trying to work this. Box screen, you know, it's like let me try.
Okay, guys, page 1. Today we're going to just review extreme value theorem and mean value theorem. We're just going to do pages 1 and 7 together. We're just going to go through these 6 problems and just review these items. I actually have a summary page, so let me do that summary page first. This is on page 3 on the half sheet here. So extreme value theorem, what is it? The purpose is to find absolute max and absolute min on a closed interval. What's the highest and lowest points across a closed interval? So the first thing we need to establish is that the function needs to be continuous on the closed interval. So we just have to always make sure that is the one condition that is spelled out. If there are any holes or if there are any asymptotes within the interval, then extreme value theorem doesn't apply and we can stop the problem. But in order for us to guarantee a max or a min, we need to make sure that the graph is continuous. It doesn't have to be differentiable, it just has to be continuous. So differentiable is only for mean value theorem and Knowles theorem. So the strategy is that we take endpoints and critical points. We find critical points, which is found by setting the derivative equal to 0, numerator and denominator if there's a denominator that exists. So reason that we want to set the denominator of f prime equal to 0 is because we need to consider places where the slope is undefined, because that could be a sharp turn, could end up being the highest or lowest point across the interval of our graph. So we find critical points, but we only consider critical points that land inside the interval. Any critical point that's outside the interval, we cross out. Now, after we find all of our all of our valid critical points and endpoints, then we plug them back into the original function, and then we just compare the y values. Highest y value is your absolute max. Lowest y value is your absolute min. Right? And actually, we don't care about the x value, so we only care about identifying the y values. Okay. All right, let's go back to page 1 here. Let's try. Okay, determine whether or not, I'm sorry, these are all mean value theorem. Oh, I had a extreme value theorem here. Sorry, the focus here has been mean value theorem. So let me go back to page 3 and go through a mean value theorem here. Okay. So mean value theorem, the purpose is to find the location on the curve where the guaranteed slope occurs. So here's our formula. I'm going to adjust the formula here. The way that I've been working on presenting to you guys is we want to find the slope information first. And then on the other side, we can find the derivative. And then we're going to work on both sides until both sides are ready. And then we'll set them equal to each other. And then we'll solve for x. Okay, so we have two conditions for mean value theorem and Rolle's theorem. It has to be continuous on the closed interval. So continuous with brackets, differentiable with open parentheses. Pretty much we don't have to worry about continuity. If it can pass the continuity condition, we can just assume that it's going to pass the differentiable condition as well. There are some exceptions to that rule, but I'll go over those later. But for the most part, these will kind of go hand in hand. If you can get that first one to pass, the second one will also pass. So first thing we do is we find the slope between the endpoints. So we do f of b minus f of a or b minus a. So whatever the slope that lands between the endpoints could be 1/2, could be 1/3, could be 6, could be 5. Okay, so we're going to find that number first. Next up, then we find the derivative function. And then once we find the slope and the derivative, we set them equal to each other. And when we solve for x, we're able to locate the place on the curve where the graph is experiencing that same slope that we found between the endpoints. And then we find our c-value, and our c-value has to land inside the interval. If it lands outside, we remove it. If it lands at the endpoint, we also remove it. With Rolle's theorem, we go through the same process. It's just that this is going to end up giving you 0 because your f of a and your f of b will end up being directly across from each other. So we go through the same process. It's just that with Rolle's theorem, this will always cancel out to be 0. And so you're always setting f prime equal to 0. But same formula, same conditions. Okay, so number 1, determine whether mean value theorem applies for the function 4 minus secant of x between negative pi and negative pi thirds. If we were to graph this function here, this will be 4 minus 1 over cosine of x. If we think about secant, secant is not going to exist wherever cosine is 0. So there's vertical asymptotes whenever cosine of x is equal to 0. And cosine of x equal to 0 at pi over 2, 3 pi over 2, any variations of pi over 2, right? And if I subtract 2 pi from pi over 2, I'm going to end up with negative pi over 2, and negative pi over 2 is going to land inside this interval, and that's going to cause an issue. The graph is not going to be continuous between negative pi and negative pi over 3, so mean value theorem does not apply. Okay, number 2, determine whether or not Rolle's theorem applies. So Rolle's theorem looks like this: f of b minus f of a over b minus a equals f prime of c. So let's figure out the well, first off, conditions, the first two conditions are good. No issues with continuity, no issues with differentiability, because with sine, there's no asymptotes and the graph is always smooth. But is it going to pass the third condition, meaning is the graph going to be directly across from each other, forcing us to get a 0 out of the slope? So let's find those endpoints. F of 2 pi minus f of 0 over 2 pi minus 0. So let's go ahead and find those endpoints. F of 0. So we have one endpoint being at 0, the other endpoint being at 2 pi. So these are not across from each other. This is going to cause the slope to not be 0. So this would be great for mean value theorem, but doesn't quite work for Rolle's theorem, because we need to have a slope 0 in order to move forward with our process. So Rolle's theorem does not apply. Since f of 0 does not equal to f of 2 pi. So we said that this doesn't work for Rolle's theorem, but it works for mean value theorem. So that's going to be basically what number 3 is. Number 3 is the same problem for 2, but it just says, does mean value theorem apply? So we'll just continue on with this problem. But I'm going to go ahead and list out my conditions, because mean value theorem, it will apply because both conditions will pass. So let's say our function is continuous on the closed interval with brackets. Function is differentiable with open parentheses. I will set up my formula here. Going to work my way down here. So f of 2 pi minus f of 0. We already found all the order pairs from before, right? So 2 pi minus 0 over 2 minus 0. Okay, so we have our slope basically figured out, 2 pi over 2, and then we have to just work on the derivative part of it, which is f prime. So sine of 2x becomes cosine of 2x times 2, and the x becomes plus 1. So 2 pi minus 0 over 2 pi minus 0, which is give us 1. So we end up with cosine of 2x. 2 cosine of 2x equals 0 because the ones cancel out. Divide both sides by 2. Okay. We do inverse cosine here. We ask ourselves, where are all the values where cosine is equal to 0? So cosine is equal to 0 at pi over 2, 3 pi over 2. We're going to keep going past 2 pi because eventually we're going to have to shrink all these values, divide by 2. So I'm going to keep finding coterminal angles, go beyond 2 pi. So if I add 2 pi to pi over 2, I get 5 pi over 2. Added 2 pi to 3 pi over 2, I get 7 pi over 2. Okay, so now if I solve for x, divide both sides by 2 or multiply everything through by 1/2. And then these all shrink down to values that now fit inside from 0 to 2 pi. So we have 4 places on the curve where the graph is experiencing a slope of 1. At pi over 4, at 3 pi over 4, 5 pi over 4, and 7 pi over 4. Across this sine graph. All these places where the graph is experiencing slope 1s. Okay. Go to page 7. Number 1, another mean valley theorem problem. All right, sine x minus x, no issues with our conditions. Our graph is continuous and differentiable, no smooth, no sharp turns, no asymptotes, no holes. So let's go ahead and state our conditions. I'll replace a and b with negative 2 pi, with negative 2 pi and negative pi. This is my a and that's my b. Okay, so if I plug in negative 2 pi into the function here, I'll get 0 plus 2 pi, which is 2 pi. If I plug negative pi into the function here, Sine of negative pi, same thing as sine of pi, which is also 0. 0 plus pi is pi. So f of negative pi is going to be pi. F of negative 2 pi is just going to be 2 pi. So we have the slope information established. We have to now focus on the derivative side of things. So f prime, sine becomes cosine, x becomes 1. Pi minus 2 pi is negative pi. Negative pi plus 2 pi is pi. So this ends up being negative 1. End up with cosine of x equal to 0. And now we can think about where's cosine equal to 0. Cosine is equal to 0 at pi over 2, 3 pi over 2. But we want to find something that lands inside this negative 2 pi to negative pi region. So I can subtract 2 pi from both of these. See if I can get something that lands inside that interval. So negative 1.5 pi will land nicely between negative pi and negative 2 pi. So I do have a solution that fits. Negative pi over 2 doesn't quite land in that interval. So okay, number 2, Rolle's theorem. Now we talked about how secant has an asymptote wherever cosine is 0. So vertical asymptote at pi over 2, 3 pi over 2. But if we were to subtract 2 pi from this, none of them will land inside that interval. So these are this interval is not going to will be between negative pi and but it's not going to impact the interval here. So so we're safe. Our function can pass the first 2 conditions. We just have to make sure that the endpoints produce the same y values because it's Rolle's theorem. So we need the endpoints to actually be directly across from each other. So we'll plug the 2 endpoints in, see what they give us. Right, so we may not recognize negative some pi over 6, but we can always add 2 pi to this to get something that that's better for us. So I can add 12 pi over 6, and I get 5 pi over 6. So secant of 5 pi over 6 going to be in that pi over 6 family. Negative x, positive y. Secant is the reciprocal of cosine. And if I do f of negative 5 pi over 6, If I add 2 pi to this, that's same thing as secant of 7 pi over 6. 7 pi over 6 is going to be in the third quadrant. Third quadrant, both the x and y are negative, so this is also negative 2 over root 3. So this fits. Our conditions pass. We can guarantee that there's going to be a slope 0 between the two endpoints. Let's go ahead and write our conditions. Okay, we know this ends up being 0 because we found the y values canceling out. We just have to figure out what f prime is. So secant's derivative is secant tangent. Now, if we're trying to figure out where this is equal to 0, we'll only care about the numerator equal to 0. Let's convert everything to be sine and cosine and just have to focus on the numerator. If we set the denominator equal to 0, that's something else. We want where slope is 0, not slope undefined. So we can think of secant as 1 over cosine and tangent as sine over cosine. But since we're looking for slope 0, we only care about the numerator. So we only care about where is sine equal to 0. So sine is equal to 0 at pi, 0, 2 pi, 3 pi. We want something that lands between negative 7 pi over 6 and negative 5 pi over 6. So negative pi will give us that location. Okay, we'll skip number 3, and then let's do one more curve sketching problem, and we'll be done. So page 11, we'll go to our calculator, graph it, and then gather all the information. Okay, the key's on page 13, but I'll work through the problem as you guys try it as well. Domain here is actually from negative pi over 2 to pi over 2. Okay, so we're going to end up with information that matches this curve. So decreasing relative minimum, increasing relative max, and decrease after that, and asymptotes at the negative pi over 2 and pi over 2. Yeah. Okay, so start off with derivative. Set the derivative equal to 0. I like to think in terms of sine and cosine, so I'm going to rewrite that as 1 minus cosine squared x. Set them equal to each other. So cosine squared x is equal to 2 cosine squared x equals to 1 if I cross multiply. I take the square root. 1 over root 2, the same thing as root 2 over 2. So we're looking for where is cosine equal to plus or minus root 2 over 2. We know it's going to be that pi over 4 family, but we only want what lands between negative pi over 2 and pi over 2. So pi over 4 and negative pi over 4. So here's my f prime sine line. Endpoints, which are asymptotes at negative pi over 2 and pi over 2. Okay, based off of our curve, we already know the shape of our graph. So decreasing slope, increasing slope, decreasing slope. So we know there's a relative minimum at negative pi over 4, relative max at pi over 4. Let's go ahead and find those order pairs. Back to the original function. Okay, we don't recognize negative pi over 4. We can always add 2 pi to this, which is the same thing as 7 pi over 4. So tangent of 7 pi over 4. Sign is going to be negative here, but it's going to be basically root 2 over 2 and negative root 2 over 2. So ends up giving us negative 1. So we have the location of our relative minimum order pair here. We know there's a relative max at pi over 4. Let's find the order pair, pi over 4 back into the original function. Pi over 2 minus 1. That's the location of our relative max. Okay, we found everything that we need to find from our derivative. Now let's move on to second derivative. Going to set it up for chain rule here. I see that squared. And you put it in a better place here. So I got to go through chain rule here. Y double prime is 2 goes to 0. We do bracket squared, which becomes negative 2 bracket to the first power. And then multiply by the inside derivative. Secant becomes secant tangent. Okay, let's get everything in terms of sine and cosine. Makes it easier for us to find our critical points. Secant is the same thing as cosines in the denominator. Tangent is the same thing as sine over cosine. So critical points can come from both numerator and denominator. If I set sine equal to 0, I'll get 0, pi, 2 pi, negative pi. If I set cosine equal to 0, I'll get pi over 2, 3 pi over 2, negative 3 pi over 2. Now, of all these critical points here, the only thing that's going to fit between negative pi over 2 and pi over 2 is just going to be 0. Everything else is going to be outside that interval. So the only critical point that we have between negative pi over 2 and pi over 2 is just going to be 0. Okay. Based off of our curve here, we already know what the concavity is going to look like. Concave up, followed by concave down. Point of inflection at 0. If I plug 0 into the function, 0 minus tangent of 0 is still 0. So my point of inflection is just going to be 0, 0. Okay, we should be able to sketch our graph here. Let me get a decimal approximation of these relative mins and relative maxes. It's around 0.5, negative 0.5. And the relative max is around 0.5. Okay, so here's my curve. Asymptotes at negative pi over 2 and pi over 2. So the graph is going to decrease. It's going to follow along this asymptote. It's going to decrease to negative 0.5 when it hits negative pi over 4. It's the point of inflection at 0, and it goes up to 0.5 relative max, and it falls after that. I give it the proper curvature here. I know there's a point of inflection at 0, 0, so concave up, followed by concave down. Okay, no homework, but when we come back from break, we'll have 2 more topics to cover. We gotta do related rates using for trig functions, and then we have 1 more set of derivative rules. Okay, and then we'll start studying for our trig unit test. All right, can we check phones? Great.
Oh, I didn't.
That's fine.
Oh, I did.
Yeah, thanks. Go ahead. What's your lunch period? Fourth, coming forth.